Hi students, welcome to physics class. Today we will discuss about electrostatic potential energy of electric dipole in uniform electric field. We have already derived the expression for the torque acting on electric dipole in uniform electric field, which is given by tau bar is equal to P bar cross E bar, which is equal to P.E sin theta. Here theta is the angle between P bar and E bar. Here P bar is electric dipole moment. Electric dipole moment, whose value is P is equal to 2A into Q. Q is the magnitude of charge in a dipole and 2A is the distance between them. And E is the electric field intensity, and theta is the angle between electric dipole and electric field intensity. We know that the direction of dipole moment is from negative charge to positive charge. The direction of electric dipole moment is from negative to positive. This is about the torque experienced by electric dipole in uniform electric field. Now, this torque is responsible for the rotatory motion of dipole towards the electric field. That is, the electric field E bar and the dipole, this dipole will align in the same direction. Electric field and the dipole will align in the same direction by the torque, which is given by tau bar is equal to P sin theta or P bar cross E bar. So this torque will align the electric dipole in a direction of electric field. Now, in order to calculate the electrostatic potential energy of electric dipole, we have to apply an external torque such that the electric dipole will rotate in a direction opposite to the direction of electric field. Let us consider the initial angular displacement of the dipole is theta 1 and the final angular displacement of the dipole is theta 2. Theta 1 and theta 2 are initial and final angular displacements of the dipole. Due to the application of external torque, this external torque will move this electric dipole in a direction opposite to the electric field. Then d theta is the infinitesimal angular displacement and there will be no angular acceleration. No angular acceleration. By the application of external torque, there exists an infinitesimal angular displacement and there is no angular acceleration. Then, due to this external torque, there will be some work dW done on the electric dipole. We know that the work done is equal to force into displacement. If the work is the gravitational force mg and s is the height, then we can say that the work done is equal to potential energy. Let us understand the concept of potential energy. If a body of mass is falling from the height h, then there is no require of any external torque. It will freely fall due to the gravitational pull. This gravitational pull is due to the gravitational force Fg, whose value is equal to mg. If we want to apply an external torque such that in order to overcome the gravitational pull, the direction of gravitational pull is towards the earth and we have to move the object in a direction opposite to the gravitational pull to a height h. Then the work done is equal to the potential energy. In the same manner, we have to apply an external torque and we have to move the electric dipole from θ1 to θ2 to an infinitesimal angular displacement d theta. Then the work done is given by, in the linear motion it is equal to F dot S. If the work done dW is equal to F into ds, when there exists a displacement of ds, small element of displacement, then the work done is also small. Similarly, this is in the case of rectilinear motion. In the case of rotatory motion, F is replaced by tau and S is replaced by, displacement is replaced by angular displacement theta. So we can write this as dW is equal to tau into d theta. This is the work done in rotating the dipole through an angle d theta. Now we have to calculate the total work done in rotating the electric dipole from θ1 initial position to θ2 final position. Then we get the total work done as integral of θ1 to θ2 tau into d theta. We have already known that tau is equal to P.E sin theta. We will substitute this value here and we get θ1 to θ2 P.E sin theta, which is equal to P.E into integration of θ1 to θ2 sin theta d theta. Here integration of sin theta d theta is minus cos theta. So we get minus Pe into cos theta. By applying the limits we get theta 1 to theta 2, that is equal to minus Pe into cos theta 2 upper limit minus cos theta 1 lower limit. Finally we get W is equal to, by rearranging the terms we get Pe plus Pe into cos theta 1 minus cos theta 2. This is the work done which is stored as electrostatic potential energy in an electric dipole. If theta 1 is equal to 90 degrees and theta 2 is equal to theta, then we get U is equal to, this term will become 0 as theta 1 is 90, cos 90 is 0, so we get minus Pe cos theta. By the definition of dot product we can write minus P bar dot E bar. We know that A bar dot B bar is equal to AB cos theta. AB cos theta can be written as A bar dot B bar. So Pe cos theta can be written as P bar dot E bar. This is the electrostatic potential energy stored in an electric dipole when placed in uniform electric field. Let us consider some cases. First one, the angle between electric dipole and electric field intensity is equal to 0. If the angle between the electric field intensity and electric dipole is 0, then we can say that tau bar is equal to Pe sin theta, whose value is equal to 0, as sin 0 is equal to 0. In the same way, the electrostatic potential energy U is equal to, the electrostatic potential energy U is equal to minus P cos theta, cos 0 means 1, therefore we get minus P. Similarly, for the angle between P bar and E bar is equal to 180 degrees, then we get tau bar is equal to Pe sin theta, which is equal to sin 180, whose value is minus 1, therefore we get minus Pe, and U is equal to minus Pe cos theta. Here theta is 180, cos 180 is equal to minus 1, minus 1 into minus Pe, we get Pe. And finally, angle between P bar and E bar here is equal to 90 degrees. In this case, tau bar is equal to Pe sin theta. Here theta is equal to 90, so we get sin 90 is equal to 0, therefore sin 90 is equal to 1, therefore we get P 1 into P, which is equal to P. And the electrostatic potential energy U is equal to minus Pe cos theta. Cos 90 is 0, 0 into minus Pe, which is equal to 0. So whenever the torque is 0, the potential energy is minimum potential energy. whenever the torque is maximum, there exists a zero potential energy. Whenever the torque is negative, we get the potential energy is positive. Here the minimum potential energy, which is given by the negative value, which shows that the system is stable. System is stable. With the positive value of potential energy, we can say that the system is unstable. System is unstable. So whenever the torque is zero, the potential energy is maximum, and whenever the torque is maximum, the potential energy becomes zero. This is about the electrostatic potential energy in uniform electric field.